Welcome back to Linear Circuits. This is Dr. Ferry. This lesson is on the current divider law. The objective is for you to be able to use the current divider law. And we can look at it from a perspective of finding the current through this branch when we've got two resistors in parallel with one another and a current source across them. The derivation of the current law is based on Ohm's law and the idea of resistors in parallel and replacing the resistors in parallel with their equivalents. The current divider law is given right here. Now it's very similar to the voltage divider law in terms of trying to find a current through one of our branches. Before, when we've done the voltage divider law, we had to find a voltage drop across a particular resistor. Here we're trying to find the current through a particular resistor. We've got this formula right here where we've got the opposite. So we're trying to find the current right through this resistor, and what we take is the opposite resistor over the sum of them times the current source. Remember, it's the opposite over the sum times the current source. Let's go ahead and derive it now. Let's recognize that we've got two resistors in parallel with one another, and I can replace them with their equivalents. Where this right here is R1, R2 over R1 plus R2, because I've got two of them. So let's call this I. Well, that's I sub s right there. And that's going in and splitting into both of these. So this is still I sub s. That means that this voltage drop here, call it V out, is equal to this resistor, equivalent resistor, times I sub s. And that voltage drop is the same across both resistors since they are in parallel with one another. So that is this voltage drop across this resistor. So from here I have that I sub 2 is equal to V out over R2. So if I just take V out and plug it in there, what I will get is this formula, R1 over R1 plus R2 times I sub s. Now, one thing to note about this is that we take the opposite resistor from the branch that we're looking at, and that means that if R1 becomes really large, this current becomes large. And that makes sense, because if R1 becomes really large, then most of the current's going to want to flow through R2 and it becomes larger. Now I want you to do a quiz. For this same circuit, I've given you numbers now, and I want you to solve for I sub 2. Now the solution here is to use a formula. I2 is equal to R1, which is 3,000, over the sum of the two, which is 6,000, times I sub s, which is 0.1. So in this case, it's 0.05 amps. And I did want to point out, whenever the resistors are the same, then the current is going to be divided equally between the two of them. So if this is 0.1, then this 0.05 makes sense. But what happens if R2 is, say, 1,000? So I've reduced the resistance for R2 and left everything else the same. Then I2 would be equal to 3,000, again, it's the opposite resistor, over the sum, which is now 4,000, times 0.1, the source, and that gives 0.075 amps. So the current actually went up. So the proportion that went to R2 got larger because the resistance went down, so more current's going to want to flow that direction. Now I want you to recognize when to use the current divider law. In this particular case, it doesn't look like what we've been looking at because I've got this resistor here. Well, that resistor doesn't really matter because this current source tells me that the current is going this way. And part of that current's going to split between this branch and part between this branch. Now these two resistors are in parallel with one another, though they don't look that way to be physically they don't look that way, but electrically they are. So the current is 0.6 going this way, and I can still use the current divider law, which gives me the opposite resistor for this branch, the opposite resistor over the sum times the current that goes into that node. Here's another case where in this case I've got 3 resistors in parallel. Actually, these two are combined right there to be one resistor. If I look at them as series, I can combine them. But I've got 3 branches right here. Now, the current divider law only allows 2 branches. So that means I'm going to have to take this part of the circuit and reduce it down to 1 equivalent resistance. And if I do that, I would find that it's equal to 50 ohms. And in this case, if I've got 2 amps going in, then it's going to be split equally between these 2 branches, and each one will get 1 amp. To summarize, we've got the key concept of the current divider law. For looking at a circuit in this configuration with 2 resistors in parallel with one another, this is a formula here where it's the opposite resistor over the sum of the 2 times the source, or times actually the current that's going into the node that connects to 2 parallel resistors. All right, thank you.